Welcome to today's press conference to Magnetic Fields and Galaxies. I'm Haley. I am the AAS Media Fellow, and I am joined by Susanna Kohler, who is the AAS Press Officer, and Carrie Hensley, who is the AAS Deputy Press Officer and is sitting over there. And so Susanna will be helping with Q&A, with running around the room with a mic, and Carrie will be on Zoom answering any, or not answering, they're going to be answering. Carrie, you can answer the questions if you want. She's going to be fielding questions on Zoom and tackling any Slack issues that we have. So there are going to be press releases distributed today for all three of our presenters, and those will be available on the AAS website, and they'll also be on the Slack. You can find them there as well, and on the usual AAS press channels. Today's videos from this morning's press conference are going to be put up on the AAS website with the press kit. Hopefully by the end of the day today, we should get those all done. So a couple of ground rules. So we are recording this briefing, and we are also streaming it to YouTube. I'm going to give a brief introduction to the topic and then introduce the panelists and their presentation titles. The panelists are going to speak in order, and then we'll go to a Q&A. For all of those participants on Zoom, if you could please type your questions in the Q&A feature, and be sure to indicate your affiliation, please, and which presenter your question is for. Same with the in-person attendees. You can type your questions in the Q&A box if you want, or you could just, raise your hand. But also please state your affiliation and who your question is for. So now we are going to start the press conference. So today we will be answering the dreaded question in astronomy: what about magnetic fields? And also we'll also be talking about, galaxies stuff. So our presenter, galaxies are really cool. First presenter is going to be Dan Clemens from Boston University with his presentation titled Large and Small Scale Magnetic Fields in the Cygnus-X Star Forming Region. And then next we'll have Erin Cox from Northwestern University with the presentation titled The Twisted Magnetic Field in a Protobinary System. And then last but not least, we'll have Melissa Morris from the University of Wisconsin-Madison with a talk titled What is the Role of the Environment in Bending the Jets of Active Galactic Nuclei? So I'm going to turn it over to the speakers.
Hi all, I'm Dan Clemens from Boston University. I will be your guide for magnetic fields and Italian food. And I hope you see the connection soon. We're studying magnetic fields in the Cygnus-X region. It is an interesting region that has a long history of being studied for its massive star formation. It's one of the nearest regions that has a great deal of material bound up in molecular clouds that will go on to form stars. And a question that we're struggling with is the role that magnetic fields play in star formation. And so we ask the question, are magnetic fields a friend or a foe of star formation? And you can see in the image, which is Spitzer in the background, and then those little polarization vectors are from our near-infrared survey. They trace the magnetic field orientations into what's called the DR21 ridge in Cygnus-X, a region where massive stars are forming. And in some of those zones, you can kind of see the magnetic field looks like it might be directing the material into the star formation regions. In others, it looks like the magnetic field is essentially stopping it, hindering star formation. Nowadays, sensing magnetic fields is fairly easy. We can do it with far infrared with SOFIA and the Hawk Plus instrument, and we've been doing it for a long time using background starlight polarimetry in the optical and now in the near infrared. And that's what I was showing here, is some near infrared data we've obtained. So here's the Italian food stuff. Is it lasagna or spaghetti? Cygnus-X, this rich star formation region that has all these massive star formation zones, the places where protostars are forming, it has a problem because it's got multiple individual clouds. and they're distributed across the field of view. And the question is, are the clouds distributed kind of like filaments tangled up like a bowl of spaghetti, or are they nice and uniform layers that are separated like lasagna? And so we've had some Herschel images here that I've been showing that call out all the different star formation regions in Cygnus-X. So this is an interesting movie that chronicles some 13 CO observations conducted by a Japanese group in Nobiyama. And what we're going to do is slide through in velocity, and you can see these different gas components show up. And so we start at a low velocity, and you'll see some regions light up and correspond to filaments, and then blow through and they're gone. And then another filament or another zone shows up, and another one, and then a fourth one. So I'll run the movie again, and you can see these at least four velocity components that are present. And many of them span across the entire field. And so we start off with this component called DR21 that picks up the bottom, and then that real star forming ridge, a very diffuse band across the front, and then another chunk, and then this final chunk. So what we can do is isolate those individual velocity features in the CO maps, and then make a map across the field that looks like this, where we've color coded the different velocity components in colors. So the red component corresponds to that DR21 ridge, and a little bit to that DR23. The green corresponds to something called the W75 velocity component. There's a blue component, and then there's even contours to identify what's called the Great Cygnus Rift, which is in front of everything. And as you can see, they're kind of tangled. And so if I were having a vote, you would probably vote for spaghetti at this point, with those different clouds tangling and colliding. And so we wanted to identify regions where the tangling was least. And so we identified zones where only a single component was dominating along the line of sight. And that's this derivative map here, where green corresponds to the DR21 component, yellow to the W75 component, and so on. But the radio information can't provide any distances in this direction because galactic rotation piles up all the velocities in Cygnus. So instead, what we've done is use those templates of single components on the sky to select stars. And so we select stars from Gaia, we match them to our own near-infrared polarimetry and to Spitzer H-band so that we can determine extinction and polarization. And Gaia will give us stars that are in front of a cloud component and behind a cloud component. And so what we look for is a step in the reddening of the clouds, the H-M color, and the polarization properties. So some stars are going to be in front, some stars in the back, and then we adjust the distance of the cloud until we get the best fit. And when we do that, we get clear indication that we have distinct layers of clouds. So this plot shows the parallax distribution functions that we find from our fitting, and it clearly separates, in this case, into 5 different distances, one corresponding to the Cygnus Rift, DR23 at a new distance, no one's called it out as a kiloparsec before, and then even W75 and DR21 are well separated in distance, much more so than their size across the field of view. So if you wanted to have your Italian food and magnetic fields, the answer is lasagna. These are distinct layers, well separated by a lot of ricotta cheese. So the clouds probably aren't doing much in the way of collisions to form magnetic field, form new stars. For us, that means we can proceed to an analysis of our Sophia Hawk Plus data, where we have, in this case, magnetic field lines that probe into regions that our near infrared cannot probe. And we can see things like pinches where the stars are forming, magnetic fields that are parallel to the ridge, and magnetic fields that are perpendicular. Now we can finally go in and pursue those without worrying, are we getting components from multiple clouds contributing? In addition, over the larger scale, then we can go after analysis of our near infrared data, for which we pick up all these regions and we get the large scale structure as well. And so with having separated the cloud components by distance, we now can try to separate them in our data and identify what the magnetic field in each of these different layers will be. So I thank you for your attention.
Good afternoon. My name is Erin Cox. I'm a postdoc at Northwestern University, and I study star formation, specifically right at the start when the protostar begins to gravitationally collapse. Today, I'm going to be telling you about magnetic fields and protobinary stars. So binary stars are two stars, essentially. So if you're familiar with the movie Star Wars, the planet Tatooine was in a binary system. And today I'm going to be talking about recent results that may show that we can use the magnetic field signature of the protostellar envelope to learn how the binary formed. So star formation begins in molecular clouds. So these are large, dusty, gaseous clouds that are large on the sky. Material begins to accumulate and the protostar begins to grow, which means that we overcome a large magnitude of scales from molecular clouds down to protostars. So this is seen on the image on the left. This is the Orion, this is part of the Orion molecular cloud seen in the filamentary structure. And each yellow dot is a protostellar system. And you see that there are two images that pop up for some of these dots. Okay. No worries, I can, oh, it's nice.
I'll just put it down there.
Cool, okay. Okay, so as you can see, for select protostellar systems, there are two images that show up. These are the ALMA and VLA observations shown in blue and orange respectively. So these are basically just different wavelengths of light for these observations. As these stars form nope. There we go. So as these stars collapse and form or are collapsing, they produce outflows. This is shown in this artist's impression here, where we observers use the direction of these outflows to anchor our observations. You also see in this image that there is this envelope structure that's feeding this disk surrounding the protostars. So there's rotation happening as mass is accumulating onto the protostar. Binary stars can be separated into two categories, wide and close. This refers to the separation between the two stars, and we believe that they are formed in different ways. Wide binaries have a separation of over 500 AU, and they're formed in the core or envelope of this protostellar nursery. So about a few thousand AU apart, the stars form and become a binary. So there's some sort of turbulent fragmentation inside of this core. In close binaries, the binaries form from the disk itself. So this is from the disk actually collapsing into two protostars. These protostars are closer. They're within 500 AU, but they're often much closer to each other than that. And this is, so this will happen at a few hundred AU. And a complication to this is that computer simulations show that protostars can actually form in the turbulent fragmentation case and move inwards, meaning that when we observe them as close, they might have actually formed as wide binaries, but we're seeing them as close binaries. And we care about this because stars and planets form at the same time. In our census of exoplanets, we see that planets exist around binary stars, but we don't know much about these Tatooine planets. If we want to learn more about them, then we must understand how protobinaries form. We had a nice introduction to magnetic fields from Dan, so I just want to show you this image showing that magnetic fields exist everywhere in space, and they thread star-forming regions. This again is the Orion molecular cloud. This is the Sophia Hawk-Plus image. And the Van Gogh-esque lines is showing the direction of the magnetic field. So you can see that they are basically everywhere. So in our study, we used a multi-wavelength, multi-scale study of the star-forming globule L483. In particular, we used 3 telescopes to do the main work: the Pico dos Dias Observatory in Brazil, the Sophia telescope, and the ALMA telescope down in Chile. We chose L483 because it's in our stellar backyard. It's very close. It's only about 200 parsecs away from us. This is a Spitzer image of L483, and you can see the iconic outflow in the east-west direction. It is also relatively isolated. So this means it's a lot easier for us to interpret our data because we don't have any competing dynamics that we have to account for. So what we saw was so I'll walk you through these images. We saw a parallel magnetic field from our near infrared data, which was from the Pico dos Dias Observatory. And that's shown in the magenta line segments on the left-hand image. So this is parallel with respect to the outflow. And then we looked at archival data and found that if we zoom in, so this was on the core size scale, so tens of thousands of AU. And when we zoom in to about 2000 AU, shown by the green line segments, we see that it stays parallel. However, our Sophia observation shown in the orange line segments and the average magnetic field from those observations is shown on the right-hand image, shows a twist. And then, surprise, we look at ALMA observations, really high resolution ALMA observations of L483, and found that it was a close binary. So at about 30 AU separation, so where Neptune's orbit is. So think if we had a star where Neptune is. And what we think happened is that L483 formed as a wide binary, and the 2 stars migrated inwards and changed the dynamics of the system, thus twisting the magnetic field. And we believe that we can use this twist as a way to learn about wide binaries that migrate closer. And we're interested in binaries because binary stars are very, very common. They make up over half of the stars in our galaxy. And again, learning about binary stars means that, and their formation, means that we can understand the types of planets that can exist around these double stars. So to recap, we use multiple telescopes to investigate the magnetic field of L483. And we discovered that the magnetic field is initially parallel, but shows a twisted morphology close to the protostars. We believe that the binary of L483 formed from turbulent fragmentation and migrated inwards, twisting the field. So we believe that we can use this magnetic field signature as a way to probe binary formation. We need to do follow-up observations of a larger sample to truly understand how binary stars form.
All right. Hello, everybody. Okay. Seems like you can all hear me. Hi, I'm the Galaxy person. We're going to be zooming out a little bit more with my talk. Also, I should probably introduce myself actually. I'm Melissa Morris. I am a rising fifth year at the University of Wisconsin-Madison. I use she, they pronouns. And I'm going to talk a little bit about some work that I've done with radio galaxies, and not just any radio galaxies, but radio galaxies that have bent jets. Now, you may be wondering, okay, what does that even mean? Well, let's start by introducing you to the radio galaxy Cygnus-A. Now, this is a very famous example of a radio galaxy. This image that you're seeing here on this slide is a radio observation, meaning we observe it at much longer wavelengths. And what we're seeing here is in the center of this image, you see a small point. Now, that small point is actually where the galaxy hosting this radio AGN exists. Now, we can't actually see the starlight from that galaxy because, again, this is a radio image. But what we do see are these giant jets that are extending far outside of the galaxy. And you see these very straight, very highly collimated jets, and we see these giant plumes of light coming from the radio emission. And so this is just an example of what a typical radio jet looks like. It has straight collimated jets. And now all of these radio galaxies are also called active galactic nuclei, or AGN. So I'll be using the two terms a little bit, but they both mean the same thing, just referring to this kind of galaxy that has these bright radio jets. So, okay, cool. A lot of radio galaxies are straight collimated jets. However, like many astronomers, myself included, not all radio galaxies are straight. In fact, a lot of them, like in this image, are actually bent. Now, what we see are a lot of different examples of different kinds of morphologies that we can see with our radio imaging. In these images, you see there is optical data over, and on top of that, overlaid are contours from the first survey. This is an all-sky radio survey. So essentially, we have a ton of these bent radio sources. Now, this kind of starts to beg the question, if we see a lot of AGN jets with straight jets, this is what we expect them to look like, then where do these things come from? Why are they so bent? Now, we have a few ideas for why that might be the case. So in this image that I'm showing you now, we're actually looking at an entire galaxy cluster. Now, in a galaxy cluster, you have hundreds to thousands of galaxies that are all really close to one another. And in clusters, you don't only have the galaxies, you've also got some stuff outside of the galaxies. So in this image, what we're looking at is you see an optical image, you see all these bright, beautiful galaxies, but you also see this purple haze in this image. And what that is those are actually X-ray observations. And what we're seeing is this really hot gas that exists between galaxies and clusters. And this really hot, really dense gas called the intracluster medium. Now, there are a lot of studies that show that galaxies in these dense environments tend to interact with this gas. And the thought is that perhaps these radio galaxies that are being bent back because as the galaxy hosting the radio jet moves through some dense gas, the jets are actually being swept back by something called ram pressure. Now, this is kind of similar to, say, a car antenna. If you're just not moving your car at all, the antenna is going to be straight. But if you're going down a highway or something, it's going to bend back from the pressure from the wind. Very similar idea here. Perhaps that's what's going on with these jets. But in order for us to really know that that's the case, it's important for us to first ask the question, where do we observe these radio galaxies with these bent jets? And that's essentially the work, or the question that my work is trying to address. How are we going to do that? Well, first, it requires us to get a big collection of a bunch of galaxies with bent jets and unbent jets. The reason why we include unbent jets is because we want to be able to compare the two environments, because if we see bent AGN, and they do in fact tend to exist in these dense environments, is that different from unbent AGN? Because, What do you say about unbent AGN if they're also in dense environments? So comparing the two is really important. And that's why we have these two large samples, both of which have come from very large all-sky radio surveys. And so what we do first is we have these samples. We know exactly where we are because we have spectroscopic observations in optical wavelengths. So we know precisely where they are in the sky, and we know what redshift they're at. So we know how far away they are from us. Now what we want to do is look around them. We want to look for galaxies that could potentially be neighbors to them. And the way that we do this is we use another all-sky survey. Yay, we love all-sky surveys. So the survey that we use to look for neighbors is called DECAL, so the Dark Energy Camera Legacy Survey. And this is a very deep all-sky survey, and it gave us a catalog with tons of information about potential neighbors for all of these galaxies. And we use something called a friends of friends algorithm to kind of find groups or find galaxies that are next to our radio galaxies. And once we do that, we are able to then finally measure the environmental properties of these radio galaxies. Are they in clusters? Are they in groups? Are they completely alone? Oh, by the way, I forgot to mention what a group is. A galaxy group is just a group of like tens of galaxies. So like a cluster, but smaller. Okay, so what did we find? Well, overall, we found that AGN with bent jets are in fact more likely to exist in larger, meaning larger on the sky, denser, meaning galaxies are really close together, and dynamically younger environments than AGN with unbent jets. Now, maybe those first two were kind of like, yeah, okay, large, dense, sure. What in the world does it mean to be dynamically younger? Well, I'm glad that I asked. It turns out if we look at this plot on the far right, what this is showing us is something called the magnitude gap. And what that means is that's the difference in brightness between the brightest galaxy in a cluster and the second brightest galaxy in a cluster. Now, why does that matter? Well, in the universe, the way things work is that big things tend to get bigger and brighter over time. So if you have a big cluster of galaxies, say you have two really bright galaxies, over time, those galaxies are probably going to merge into one really big galaxy. And that really big galaxy is going to continuously consume other galaxies and smaller galaxies such that it's going to get brighter and brighter and brighter. And then it's going to be much brighter than the next brightest galaxy. Hence why we measure the difference between the brightest and the second brightest, or the third brightest, or the fourth brightest galaxy. If that brightness difference is low, that means that this group was probably dynamically younger. It hasn't had as much time to really consume all of those other galaxies and get big enough such that there is the really biggest cluster or group galaxy. And so what we find is that bent environments tend to have lower magnitude gaps, whereas unbent environments tend to be much higher. So they have settled down a lot more. And so this kind of goes along with, and this really supports our theory that we were mentioning in the beginning, that it likely is all of that gas and dust that exists in these environments that is, in fact, bending these AGN jets. And so now that we have a pretty good idea of what the environments of these bent AGN jets look like, we know that they're in really dense environments. Some work that can be done and is actually actively being done is we can use them as tracers of groups or clusters. It turns out it's actually pretty hard to find a group or cluster unless you have a lot of spectroscopy. So ways that we can do that are finding these AGN and finding these bent AGN specifically. We can also make indirect measurements of the density of gas in these dense environments. I showed you a very beautiful image a few slides ago of this X-ray image of this galaxy cluster. You could really clearly see all of the gas. Turns out most galaxy groups don't really have the same X-ray data available. We don't really know how much gas exists in them. And so this can be one way for us to actually observe that gas, is by looking at these galaxies and using them to measure how much gas there is. And so that's going to be where this group heads from here. And last but not least, we can also study how galaxies in similar environments evolve over time. So that's all I've got for y'all today. Thank you so much.
Okay, we're going to move to a Q&A now. Just as a reminder, if you're on Zoom, please type your questions into the Q&A. And for everybody in general, if you have a question, please identify yourself, state your affiliation, and state who the question is for, please. So we're gonna have Carrie monitoring the Q&A on Zoom, and then once Susanna, once we get the, okay, we good? We good? Where's our other, oh, there we go. Yeah, go for it. Okay. And Susanna will be running around with the microphone. So just raise your hand if you have questions. Again, affiliation and who your question is for, please. Okay, so these are live. I turned it off earlier. Please stand by. And we already answered the question, what about magnetic fields? You can't ask that. Dan, I'm just glad your talk was after lunch because I think the spaghetti and the lasagna would have made us really hungry. I had heard of nuclear pasta before, but not like that kind of lasagna and spaghetti. So it was very engaging. You should have like had that in your title. Definitely would have been like, yeah.
It's actually in the press release title.
Okay, good. Okay, it's in the press release title. Awesome.
Anybody with a question to maybe come up here and speak into this microphone?
We're adapting.
Govert Schilling, freelance from the Netherlands, with a question for Dan. You answered the question of whether or not magnetic fields are the friends or the foes of star formation. Now, do your results on the Cygnus-X region with the separate velocity fields, does it imply that they're neither? And also, I was wondering, suppose there are no intergalactic magnetic fields at all, what would that mean for star formation in the Milky Way?
Good question. I'll do the first one first because it's a little easier. I will try to speak into that one. It is our day for technology. We haven't yet separated the magnetic fields into the individual components yet. The first step was to establish distance and make sure that the components are not interacting. So the answer to your first question is come back in about 6 months and we'll have an answer for you. The second question having to do if there were no magnetic fields in the universe, what would our conversation be? And the answer is we wouldn't be having it. Magnetic fields seem to be very important in star formation, whether it's ordering disks to form or channeling the gas from the disks onto the protostars. So no magnetic fields, no discussion.
Hi, I'm Jeff Baumreining with Caltech. I have a question for Erin. I was wondering if you had any idea or an estimate of the time scale that it would take for the magnetic field to change in this binary star case.
Yeah, that's a good question. So I don't have an exact answer for how long it takes for the magnetic field to change. So we are looking at what we call a class 0/1 target, which means that it's about 100,000 years old. So up to that amount of time.
Thank you, Rick Feinberg from the AAS and Sky and Tel. This question is sort of for Dan and Erin both. So stars form from cold molecular gas, right? And you're talking about magnetic fields, but presumably the cold gas is neutral. So my question is, at what point do the magnetic fields become important in the process of forming your stars in a star formation region or a binary star? And are they just, are they intergalactic fields or intragalactic fields, interstellar fields that get compressed and twisted, or are the fields generated somehow in the star formation process?
I'll deal with the large scale, let Erin deal with the smaller scale. On the large scale, we think that magnetic fields are important in the way interstellar gas and dust gets concentrated into the molecular clouds that we think of as forming stars. And so just the act of getting those molecular clouds collected may involve magnetic fields. And yes, they're mostly neutral, but the ionization fraction is just high enough that the fields are largely frozen into the material. So it acts like a weak plasma. And as the cloud collapses, drags the field with it, and doing so amplifies it to some degree until we start to form a cloud core, and then I turn it over to Erin.
Yes, so we see that the field is dynamically important until about maybe the protostellar envelope. And then there's really active research about how important it is. So some of the sources that we look at, we see magnetic regulation in terms of whether a large disk can grow or not, and whether the magnetic field has hindered that. That is a really good question though, because every few months a paper comes out saying it's one way, and then a few months later it comes out saying that it's another way. So I think we're really at a point where we have a lot of observations, and we need the theory now to like really match what the observations are showing, so we can really nail down these like small details.
Do you get any clues from simulations that, I mean, presumably all of these observations that show it's one way or the other are being tested against simulations?
Yes, we definitely get clues from simulations. The difficulty with using simulations is that they're not able to put in everything that we know occurs. They're very computationally expensive. So people have to get rid of some aspect of the physics that's happening just in order to perform the simulation on a reasonable time scale. But we are in a golden age for computer simulation. So they are coming out with really, really nice data.
Hi, I'm Sumit Kulkarni from the LA Times. I have a two-part question for Melissa. Thanks for a very nice presentation. Have you seen any association between the degree of bending of these chests and the size and the density of the clusters? And now that you have about 100 or so of these observations, each potentially linked to a cluster, how is that going to change the large scale structure and evolution or understanding of that for the universe?
Great question. So I'll answer the first one first. And I hate to say that that's not exactly something that we do in this project. So just clarifying, are you asking like how bent a galaxy is versus, okay. So that's not necessarily something that we've done just yet, but that is something that we're planning on working on in future work. And as part of, I mentioned briefly talking about being able to measure how dense a cluster or group is. And part of what goes into doing that is actually measuring just how dense the jets are. And so that is going to be something that will come in the future. So keep an eye out. And I'm so sorry, I already forgot the second question.
Yeah, it was now that you have more than 100 such observations of these jets, each potentially linked to a cluster that hasn't been observed by other means before, right? So is that going to change our understanding of the large scale structure of the universe and its evolution in general?
Right. So I can't say with full confidence that none of these things, like none of the clusters have necessarily been observed before. This is the first time that we're like associating event AGN with them. As far as how that kind of changes our idea of how they evolve over time, I think it has a lot of it has the ability to really kind of help us understand how much gas is in these environments and how much, like understanding how much gas is in these environments. It sounds kind of lame, like how much gas is not inside of a galaxy, but it's actually a super important question when it comes to understanding how galaxies stop forming stars in really dense environments, because that's one of the really big open questions that is in astronomy right now. Like, how does, we call it quenching, how does the quenching of star formation really happen in these dense environments? And there are all sorts of different quenching mechanisms or ways in which galaxies can stop forming stars. And a lot of the times those do depend on how much gas there is in these environments, because you have the gas in the galaxy interacting with the gas outside of the galaxy. And the gas in the galaxy, as we learned, it is what is responsible for forming stars. But how does that interaction happen? I don't know, kind of hard to say if you don't know how much gas is there. So, it's all kind of related, and that's where Venn doubles can be a really helpful tool to help us understand that. So, yeah. Thank you.
Martin Radcliffe, freelance, and Evans and Sutherland. Quick question for Melissa. Can you tell the difference between, radio jets are produced over a very, very long time scale because they go out millions of light years far beyond the galaxy. So how can you tell the difference between ram pressure and then I'm trying to imagine the change of orientation of a galaxy that's undergoing strong mergers with multiple other galaxies, and so it's causing a tip in that jet, and it might be a result of a merger rather than what I would think is a gentle ram pressure. The merger might create quite a sudden change, relatively speaking. How can you tell the difference?
That's a really great question. So a lot of the times if you have like something with a merger would have a lot more, it would be big. So okay, one characteristic of all of these bent AGN is that they're very smoothly bent and the jets are bent in the same direction. So you don't have a lot of like S-shaped AGN or anything like that. I mean, okay, I'm not saying we don't have them because they do exist, but they're not what I'm studying. A lot of the time something like that is due to the way that the AGN itself moves within the galaxy, because sometimes it can kind of shift and wobble around. We call that precession. And we can see something like that, and that causes some other kind of S-shaped jet. And we, again, like I said, we do see those, but those aren't things that we really consider in our sample. As far as galaxy mergers, because these mergers tend to be pretty, well, like there's a lot of things dynamically that are going on with the galaxies. And so I don't know that I would necessarily expect the AGNs to be bent too much. Even if they were bent in a merging situation, then you would still need some other dense medium surrounding those galaxies for there to be a merger. So does that answer your question? A little bit. Okay.
Did you want to follow up?
Yeah, if there's follow-up, I can.
I don't really have a follow-up. I mean, clearly it's a very complicated situation, but as you were talking, I was thinking, a merger event over the lifetime of a cluster of galaxy is quite short. So you might only see short bends that would gradually get smoothed out over the interaction with the IGM. as the galaxy is moving around and precessing as you're talking about. So maybe that partial, I don't know, did I answer my own question?
I mean, you can get merging of like two separate groups as well. And that can also kind of lead to some fun dynamics that can lead to bending. And that's kind of what goes into a little bit of like the yeah. Thank you.
I have a question here from Bill Waller of the Galactic Inquirer and Doc Waller's Earth and Space Reports YouTube series. And I assume this is directed to our magnetic field experts in the room, at least the ones on stage. What will be missed in diagnosing magnetic clouds when Sophia goes away?
Thank you for your question, Bill. I notice we have some Sophia folks in the audience. At the moment, Sophia with a Hawk Plus instrument is the premier instrument for probing magnetic fields in high density regions. And so we're going to lose a lot. The near infrared polarization we can do cannot see into those zones. It's really only up to Sophia and the Hawk Plus instrument. So losing that is going to be a huge loss.
No, I just agree that losing Hot Plus will be a sad day for the community.
Any more questions from the audience? Got plenty of time.
I think we're good to end a bit early.
Alrighty, well, I just wanted to thank all the speakers for their wonderful presentations. Thank you to the audience for your attention. Thank you to the public information officers who helped with the press release and the briefing prep. Thank you to USRA and our other sponsors. And our next press conference will be tomorrow at 10:15 a.m. Pacific time in this room, titled Nearby Disks, Faraway Galaxies, and a Record-Breaking Star. Hope to see you all there.